Thank you very much. And so after this high energy physics, let's go back to the cold astrophysics and the cold universe. So in just 2 years of operation, JW has provided an incredible amount of data and high quality data that allows me to be here today to talk to you about super early galaxies. By super early, I mean galaxies that are located at redshift larger than 10. So this is quite amazing, and only 15 years ago I could only have dreamed of being here today and giving this talk. So, but all this fantastic data generated puzzles and discoveries. So we have already heard about many other discoveries during the first part of this conference. Today I would like to concentrate on one discovery that I feel is particularly important, and basically can be summarized as follows. So we are finding an unexpectedly large number of luminous galaxies at these early epochs, and these galaxies, quite surprising, not only tend to be massive, with massive larger than 10 to the 9, but they also have blue colors. This is something that we are not used to in the lower redshift universe. And somewhat consistent with all this, at least for the few of them for which we have tried to look if there is gas or dust with ALMA. So far, they have escaped our detection, and even more surprisingly, even after 80 hours of observation with NOEMA, which is not ALMA, of course, but still, it's a very nice radio telescope, in GNZ11, we only have upper limits on the dust continuum. So apparently, dust may not be there. So how do we understand all this? So in order to make a large number of luminous galaxies, of course, you want to increase the luminosity in a way or the other. So there are several ways in which you can increase the UV luminosity, as a result, because this is the result of 3 different factors that are producing the observed luminosity. These are the star formation rate, the absorption coefficient in the UV, and also the dust attenuation. So there's been several proposals. For example, some have suggested that we can increase the star formation efficiency or have a large stochastic star formation rate that produces bursts of star formation. Or we can change the mass distribution of the stars and also their production efficiency, for example, using metal-free stars or pop-3 stars, or even pushing the IMF towards the massive end regime, so a top-heavy IMF. Or finally, we can also use the dummiest solution, which is, okay, if you want to have something bright, remove everything that is attenuating it. And so removing dust attenuation for sure the simplest thing. And so the way in which I decided to proceed is the following. So let's see whether the simple solution works. If it doesn't, let's go to the next step. So let me concentrate also for a matter of time today on this third and my favorite hypothesis, even though I'm totally open to all the other 2. So there's been signs from the very, very beginning of the JWST observations that there was a clear trend between the AV, the attenuation in the visible, and the redshift of the galaxy, particularly because 2 years ago, which seems ages ago, we were coming from the observation of the rebel galaxies of redshift 7, which are moderately absorbed, but we were noticing that indeed the first galaxies that were detected by JWST have AV below 10 to the 1%, so extremely low attenuation. Of course, there's been a lot of work, and we have heard already also from done before that there is a clear trend of beta decreasing with Z, and even we have a very nice fit with very blue colors, sometimes also being well below the stellar nebular limit. So apparently these galaxies indeed don't have dust, but here is the problem. So why don't they have dust? Actually, the expectation would be just the contrary. And in fact, I was asking myself, why aren't they obscure? Because if you do a simple estimate, but you can repeat this on any of the JWST galaxies, take one as an example, redshift 12 is called GSZ2. Castellano 23. So the mass of this galaxy is 10 to the 9.2. So if you say, if I see these stars, and I know the stars form dust through their supernovae, then if I use the same dust-to-stellar ratio that I observe locally, and also even higher, I have to say, in the rebus galaxies, then I would expect to have 3 times 10 to the 6 solar masses of dust. But now, remember that these galaxies, as we have just heard, are incredibly small. They go down even 20 parsec, as we have heard. So if you say that these sizes are small, and then you want to compact that amount of dust in such a small volume, then you would expect to have an optical depth in the UV that is of the order of 25 times this factor. What we observe instead, as I told you, is less than 1%. So they are 2,500 times less opaque than what they should be. It's an incredible number. So I said, if dust is not there, but the stars are there and they must have produced this dust, where is the dust? So could have the dust been ejected instead by what? By radiation-driven outflow. That's my hypothesis. Why do I think that this is the case? Because you can work out very simply that if you have a luminous source, compact source, that is producing a lot of UV radiation on the surroundings, it exerts a radiation pressure that is extremely high, and it could be even super Eddington in the sense that we normally use for quasars, for example. So the Eddington parameter larger than 1, meaning that the radiation force is stronger than the gravity force, you can show very easily that is equivalent to require that this galaxy has a specific star formation rate larger than 25 inverse gigayears. Now, this number is clearly uncertain because it depends on the dust properties and many issues, but zero order level, you may say that whenever the specific star formation rate is high, then the galaxy tends to be super Eddington and therefore drive a wind or an outflow that is clearing the dust. So this is my simplest model. Galaxies are attenuation free, so they are blue. And this attenuation-free condition is related to the presence of an outflow. This is what I call the attenuation-free model, as simple as it is. And the model.zip is summarized here. So I'm assuming that the star formation rate is an efficiency times the gas mass, which is FB, the baryon fraction, times the halo mass, divided the free fall time. The free fall time, by definition, is in cosmology, is basically, you can show it, it's 6% of the Hubble time, very easy. Then you can compute the stellar mass in the simplest possible way. You say that most of the stars are formed within the last free fall time, which I show you later, that is also not so crazy. And so you can compute the specific star formation rate, which is a key ingredient, as I told you in the previous slide. And finally, you allow for an outflow to develop whenever the star formation, the specific star formation rate exceeds some threshold. You do this simple exercise, you work out your model, and then you can predict a number of things. And this is a collection of things that I could predict that are published in the papers that I wrote in the last year or so. So we can compute the UV luminosity function of redshift 11, the UV luminosity function of redshift 12. So this is the redshift 11 curve predicted. These are the data. This is the redshift 12 predictor. These are the data. You can produce the cosmic star formation rate density. You see that because there is no dust, you get naturally this enhanced cosmic star formation rate density that is somewhat flatter than we were thinking before JWST. And finally, you can also have the number counts, which nicely predict that at redshift 13.5, you should have 2 galaxies by chance. In fact, we only have 2 galaxies around redshift 14. So please don't discover other galaxies because, because that, okay, thank you. So now, this is a nice test, but these are tests that I'm sure that at least half of the people here in the room, they could also fulfill. So the statistical tests, luminosity functions and number counts are okay, but they're highly degenerate. So you can produce them by playing around with parameters. So they are not particularly stringent. Now, I think that we are used to the scientific method, which is based on the idea of testing models. So that's the way in which we have learned from Galileo Galilei, a scientific method, and by the way, yet another member of the Italian mafia. And so this galaxy is, so let's concentrate on something which is more difficult. So the JWST 14 at redshift 14.3, the most distant galaxy. What is the most stringent test? Reproduce the star formation history of this galaxy. We have spectra, we have all the properties that we want, so it's a perfect test bench for all theories. Okay? So let's see what the AFM model then predicts. So this is a very busy slide, and it's the last slide, so let me take 3 minutes to explain it quite simply. So you have a log of different quantities as a function of look-back time. The galaxy sits here, and so which is redshift 14.3, and this we are going back in time. So the first curve is the blue one, is the star formation rate that I predict for this galaxy. So the galaxy starts in the first phase of bursting mode, in which the star formation grows, but then it stops. It started at redshift 26, and then it stops after about 40 million years. Why is that? Because the first stars that form here increase the intensity of the UV radiation in the galaxy. And so the UV radiation destroys molecular hydrogen, and so there is no molecular hydrogen to power star formation rate. So the galaxy comes to a halt. And then it starts again, it tries again, second trial, and then fail again. But in the meantime, the dust content is increasing because the stars are forming dust and metals, which tend to shield the gas from the UV radiation itself. And so you see there are phases in which then the dust-to-gas ratio increases, then decreases because of a cosmological accretion, and then it follows like that. So at some point, there is enough dust so that the galaxy can start the main star-forming phase. Up to this point, it only formed about 1% of the final stars that we observe. So during the final star-forming phase, in which the galaxy has a star formation rate which is quite smooth, then the galaxy becomes rapidly obscure, and it stays obscure for about 40 million years, because it's building its own dust, and there's no way to avoid that, provided you have star formation, okay? Because star formation also produces dust. At some point, though, the galaxy becomes super Eddington, and it develops an outflow that decreases the star formation rate from, say, 100 solar masses or so down to the level of 20 or so that is measured at redshift 14, and this model, as simple as it is, can reproduce essentially all the properties of the galaxy, from the slope, UV, UV radius, stellar mass, star formation rate, AV, metallicity. So it's all there. So you don't need to play around with that. If you take this star formation history and you plug it into your favorite SED code, you can produce a spectrum. This is the spectrum that is predicted from that model, and you can compare it with the data. So to me, this is a stringent test. So the spectrum that you see is this one, in which you have carbon-3 and also prediction for other lines, and you can compare it with the one that is observed. It looks quite nice, and even there is an indication of a 3.6 line. So I think that this is the way to go, and the way to compare theory with data according to our scientific method. And this is my summary, which basically says that this simple attenuation-free model can explain many properties of the early galaxies, provided that you allow for the galaxy to be clean by outflows of the dust content. And so there are also implications for quenching and Lyman alpha escape, and also peculiar abundance ratios. Thank you very much.
Thank you, Andrea. And we have time for a few questions.
Thank you. Can you tell us more about your mass outflow rates and how that may change with mass and redshift?
Yes. So the outflow, but for this particular, I can tell you for this particular galaxy for which I have the number in mind is about 150 solar masses per year at the time, right now, at the time of observation. It's been, sorry?
You have many galaxies in your model. How does it change with mass and redshift?
I can, it depends on the specific star formation rate. So the higher the specific star formation rate, the higher is the mass outflow, because as I was telling you, this is the key parameter that is governing whether the galaxy has an outflow or not. So if you increase that on average, but you can find the formula in the paper, or we can discuss it. Sure, sure. Yeah, it's of the order, well, for galaxies like these ones are of the order of 100 solar masses per year, say, but it varies in time, it's not constant.
Sure. Priya?
Priya, very nice talk. I was curious, so what jump starts the star formation for the specific SED that you showed for this object?
At the beginning, sorry, we jumped, or?
So you have the star formation rate that stops, and then you start up again.
Yeah, it's the Lyman-Werner feedback. So basically, as you start forming stars here, you see that this is the intensity of the Lyman-Werner background that is killing the molecular hydrogen. So it goes up, and then when it passes a certain threshold, it's like the direct collapse black hole, right? So then you kill the molecular hydrogen, and then you have to wait for the stars to become older, and it goes down. When it's below a certain threshold, you start again. But you can only stop this process when you have enough dust.
There's a floor and a cap. Okay.
Yes.
Okay.
Yes. Well, there is a threshold. So, yeah.
By the way, sorry, but since you have said that, at the Lyman-Werner, well, it depends on the Lyman-Werner flux actually, but if you suppress H2 cooling and you still have a metallicity of 10 to the minus 3, you may have very different IMF.
It could be. For sure.
IMF.
Absolutely, yes.
So this, I think, boils down to this argument that comes from like Roman Empire times, right? So it's actually how dust is produced. So if it's all produced by stars and then nothing happens to it, then yes, there's a problem. But if actually dust grows in the ISM, there is no problem at all because there's no time to grow at those metallicities.
Right.
Absolutely.
So they don't actually need any kind of attenuation. It's attenuation free because there's just dust doesn't appear at all in those
Well,
growths.
if you allow for, I'm agnostic about dust growth, I mean, fine. But the question is that if you allow the dust to grow, you would expect even more dust.
No,
so it would be even more obscure, right?
No, the point.
Well, fine. In fact, I'm not assuming that it is growing. I say there's no growth. But if you would allow growth, which in principle should be there, you would have even more dust. And so the problem becomes even worse.
No, the other way around.
Why?
Because if you liberated it on local galaxies, in which there is growth.
Who's calibrating? I'm not calibrating.
It's number like 10 to the 6, right? It's a dust to stars ratio in the Milky Way, but it's all because of growth.
I think that this is clearly an argument of discussion for this activity.
Particularly with Nick.
With Nick, with me, with many others. So Mark, you wanted to... We have just time for
Mark Dickinson.
1 minute more.
I guess back to this, the restart and the Lyman-Werner and everything. I mean, is there any reason why, I mean, you have it drawn here with the first episode, a second episode, and then it goes into this continuous. I mean, could it be sputtering repeatedly before it finally catches fire and keeps on going? I mean, or is there some reason why it should happen twice?
No, for this galaxy, it happens twice.
Okay.
But it depends on the property. But there is a bursty phase, initial bursty phase, which is due to the fact that you form stars, but then the UV becomes too high in order to produce more stars. Then you quench. Then you start again. And that continues. In principle, if you have no dust, in principle, it will continue forever. Right? But at some point you build up a little bit of dust at any little burst that you're making, and so the dust that you produce is at some point sufficient to shield the gas, because star formation rate depends on shielding. The gas has to be self-shielded. And so the number of bursts depend on this process, which is a complicated one.
So I guess my other question, you know, thinking of the kinds of pictures that Avishai was showing in which he focuses on the fact that star formation is happening, you know, you're sort of, I think, treating the galaxy as monolithic in this sense.
Absolutely,
as
yes.
opposed
but
to a bunch of star clusters.
They're very small.
Yeah, but it may still have a bunch of star clusters within it. And so I'm wondering, you know, would you get the same kind of synchronization if you broke the galaxy up into lots of bits within that small galaxy?
I mean, I can't answer that question. This is not embedded in my model. I think that given the fact that the sizes are 100 parsec or even less sometimes, it's very hard for me to understand there is so much complexity in this such tiny region, even though you could have, I mean, sure, there are subclusters of stars that are forming at the same time, but after all, I don't think that compared to the global extent of the gas and the virial radius of the galaxy, this is a region that could be broken in other pieces without and changing the entire scenario simply by that.
Okay.
This particular redshift 14 galaxy is quite large for,
260 parsecs.
Yeah. So, I mean.
So, yeah. So let's thank Andrea again. And